Hi, I'm Ishtiyaque, a third-year PhD student at University of California, Santa Barbara. Today, I'm going to talk about Coeus, a system that allows you to search for documents from a public repository like Wikipedia without anyone else, not even the document server, know about your search keywords or the document that you retrieved. Building a system like Coeus is important because information on search keywords and retrieved document leaks privacy. As a motivating example, let us consider Ziv, who identifies with a non-binary gender and wants to keep this information private. Ziv is planning to attend a gender-specific event and wants to know about the event beforehand. So Ziv opens up Wikipedia, which is a popular to-go place for knowing about something, and types some keywords in the search bar. These keywords are sent to Wikipedia server. In response, the Wikipedia server sends a ranked list of documents that match the keywords. Ziv selects one of those documents and reads that document in details. However, in this entire pipeline of searching and retrieving documents, there are several privacy concerns for Ziv. For example, an internal or external attacker may compromise the Wikipedia server and know about Ziv's keywords. Also, internet service providers or a network eavesdropper may compromise the network and see the retrieved document by Ziv, which will leak the preference of Ziv. So the question is, can we enable Ziv to search and retrieve documents privately from Wikipedia or generally from any public cloud server privately? Searching documents privately has got a lot of attention in the literature recently, but unfortunately, the existing techniques cannot solve Ziv's problems. A very popular technique for accessing documents privately is Oblivious RAM or ORAM. ORAM requires arranging the data in a particular tree structure and shuffling the data after every access. This is more suitable for the case where the data is owned by the client. But we are targeting an application where the data is owned by a public server, which serves a lot of different clients. So ORAM cannot be used in this context. Another interesting relevant technique is private information retrieval or PIR. PIR allows a client to retrieve an element at a particular index from the server obliviously. But PIR requires the client to know the exact index of a document in an array of index in the server. So it does not support search with keyword. An extension of PIR supports searching with keywords. However, PIR with keyword can return only a single document that contains that particular keyword and does not support ranking, which is very important in this context. To address the challenge of ranking, there has been some work in the context of private documents using homomorphic encryption. In principle, these works use a two-round protocol, which also can be extended in the context of private documents, public documents. I will briefly discuss this two-round protocol, which acts as the starting step of Coeus. The first step is for query scoring, where the client interacts with a query scorer. The query scorer contains a TF-IDF matrix of all the keywords in the document server. The client first constructs a query, which is a binary vector encoding of the search keywords and encrypts that. This encrypted query vector is sent to the query scorer. The query scorer performs a secure matrix vector multiplication with the TF-IDF matrix and the query vector to generate an encrypted vector of score corresponding to each document relevant to the keywords. These encrypted scores are sent back to the client, who can decrypt that and find out the top K scores. The client stores the top K indices of the scores. Then in the second round of document retrieval, the client uses these indices to retrieve the documents using PIR. So client encrypts the indices, sent to the document provider. The document provider performs PIR to generate an encrypted vector of the corresponding documents and send the encrypted documents to the client. The client can decrypt and select one of them to read in detail. In principle, this two-round protocol can provide unconditional privacy to Ziv. However, the problem is this two-round protocol has very high overhead. We evaluated this two-round protocol for 5 million documents in the English Wikipedia dataset, and the end-to-end latency came out to be 93.92 seconds, out of which 63.39 seconds are for query scoring and 30.53 seconds are for document retrieval. Evidently, this is not very interactive. So we asked the question, can we do better? The key challenge to this problem is the server needs to process the entire state of the system for serving every query. That is, the query scoring server must touch every element of the several hundred billion elements in the TF-IDF matrix, and the document retrieval must process every bit of the 5 million documents. This is because if the query scorer or the document provider excludes a subset of their data, an adversary can know that Zip's query doesn't concern that part of the data and thus break the privacy. We cannot break this fundamental lower bound of processing, but we can identify system bottlenecks and can make particular operations optimized. With this principle, we designed and developed a new system, Coeus, that reduces this end-to-end latency to 3.9 seconds, out of which 2.81 seconds are for query scoring and 1.09 seconds are for document retrieval. Coeus achieves its performance with two key ideas. The first idea is a new 3-round protocol instead of a 2-round protocol. And the second idea is an efficient algorithm for large-scale secure matrix vector multiplication. Now I will go into details with these two ideas. To understand the utility of a 3-round protocol, let us zoom into the second round of the 2-round protocol, that is document retrieval round. In this round, the client interacts with the document provider using multi-retrieval PIR and retrieves K documents from obliviously. There are two major issues with this round. The first issue is, even though the client consumes one document eventually, the client retrieves K documents, which is more costlier. And the second issue is PIR requires all the documents in the document library to be of the same size. In order to do that, we need to pad all the documents to the size of the largest document in the library. So after padding, the document library looks more like this, which increases the PIR cost drastically. To address these issues, we construct a new metadata library for each document in the document library. The metadata for each document consists of the title and short description of the document. The goal is the client should be able to decide which document to read in detail just saying this metadata. And using this metadata library, we extended the 2-round protocol to a 3-round protocol, where in the round 2, the client interacts with the metadata provider and retrieves K metadata instead of K full documents. And then in round 3 of document retrieval, the client just retrieves a single selected document from the document provider obliviously. As a result, the more costlier multi-retrieval PIR is performed over the smaller metadata library. To address the second issue of document packing, we take help of bin packing. Instead of padding each document to the largest document size, we can pack multiple documents together in a single object, where each object is equal to the size of the largest document. As a result, the size of the document provider gets reduced by a large factor. However, now the one-to-one mapping between the document ID and its location in the document provider is broken. But we can piggyback this index information with the metadata for each document. As a result, the client will be able to know the exact index of a document in the document library. For our dataset of English Wikipedia, this bin packing reduced the size of the document library by a factor of 50. It is important to note that this bin packing is not possible for the 2-round protocol. With this 3-round protocol, we could reduce the document retrieval cost to 1.09 seconds from 30.53 seconds. The second idea we used is devising an efficient algorithm for large-scale matrix vector multiplication. Existing works using secure matrix vector multiplication deal with several millions of elements. However, in our case, the main challenge is the TF-IDF matrix consists of several hundred billion elements. And to address this issue, we devised 3 optimizations on top of the state-of-the-art Halevi-Shub algorithm for secure matrix vector multiplication. We first removed redundant calls to an expensive homomorphic rotation operations. Then we amortized the cost of homomorphic rotation by reordering the operations in Halevi-Shub algorithm. And finally, we distributed the workload among a cluster of machines efficiently. The details of these techniques are available in our paper. And using these techniques, we could reduce the matrix vector multiplication cost to 2.81 seconds. To summarize, hiding search keywords and document retrieve is very crucial for privacy. Coeus provides Oblivious document ranking and retrieval over public data without any trust assumption. And Coeus can achieve an end-to-end latency of 3.9 seconds over 5 billion documents in English Wikipedia with two key techniques. The first technique is a three-round novel protocol. And the second technique is an efficient algorithm for large-scale secure matrix vector multiplication. With that, I conclude. Thanks.